Hello and welcome to The Explainer. I am absolutely thrilled to have you here today. If you're someone who loves figuring out how the world works from the ground up, well, you're in the exact right place. Today, we're diving headfirst into the fascinating world of optical biosensors. We're going to uncover the brilliant unseen science behind something that millions of people rely on every single day, and we'll break it down step by step. Okay, let's dive into this. How exactly does a simple paper strip read your blood? I mean, on the surface, a modern test strip just looks like a tiny, basic piece of plastic and paper, right? But beneath that super simple exterior is an absolute microscopic marvel. It's literally a highly engineered biomedical laboratory that's been shrunk down to the size of your fingernail. Today, we're unpacking exactly how that tiny lab functions. Here is our roadmap for today. We'll kick things off with the magic of colorimetry, peek inside a test strip, and explore the chemistry of color. Then, we'll look at how we actually read the results, take a trip back to the early days of glucose testing, and wrap up with the incredible shrinking drop of blood. Starting right off with Section 1, the magic of colorimetry. We're focusing today on colorimetric test strips. This is a widely established, somewhat low-tech, but incredibly reliable method. Basically, these are disposable, single-use cellulose pads, or strips, that are deeply impregnated with specific enzymes and reagents. And the absolute most common global use for this incredible tech? Whole blood monitoring, specifically for diabetes control. By simply putting a drop of blood on a paper strip, people can monitor incredibly complex biological markers right in their own homes. Moving on to Section 2, inside a test strip. You see, this isn't just a single flat piece of paper. It's a beautifully layered system designed specifically to move fluids. On one end, you have the sample pad. That's where the liquid is first applied. The fluid then travels through a conjugation pad and glides right across a nitrocellulose membrane. Notice those vertical red lines right in the middle? Those are your test and control lines. Finally, the fluid ends up in the absorption pad, which acts just like a sponge, pulling everything across. And all of this is mounted on a sturdy backing card. It's essentially a perfectly engineered microhighway for fluids. Section 3, the chemistry of color. Now, what's really interesting about this is the core concept of a chromogen. The vivid color you ultimately read on a test strip isn't just sitting there waiting to be uncovered. It actually has to be created from scratch. A chromogen starts off as a completely colorless or maybe extremely faintly colored chemical compound. It only turns into a brightly colored compound, known as a chromophore, when it goes through a very specific chemical reaction. There is a brilliant chemical relay race going on here that makes glucose testing possible. When the blood hits the strip, an enzyme called glucose oxidase causes the aerobic oxidation of the glucose in the blood. This reaction produces hydrogen peroxide. Then, that hydrogen peroxide is passed like a baton to the next stage. A second enzyme, horseradish peroxide, uses that newly created hydrogen peroxide to oxidize our weak, colorless chromogen. The result? A highly colored dye and water. The more glucose you have in the blood, the more hydrogen peroxide gets made, and the deeper and darker the final dye becomes. Just to make this super concrete, here is what an actual chromogen looks like. On one side, we have the chemical structure for a compound called 3,3-diaminobenzidine tetrahydrochloride, which is universally and thankfully just called DAB. On the other side is how that translates into the real world, a physical tablet of DAB ready to be dissolved and used in a lab. This is exactly the kind of colorless compound waiting inside the test strip, ready to be transformed. Which brings us to Section 4, reading the results. So once that dye is produced, there are two primary ways these strips are evaluated. The first is through portable reflectance meters. These use electronics and light to measure the specific, precise shade of color on the strip. The second method requires zero electricity whatsoever, direct visual comparison. Just like you might remember reading a traditional pH strip in high school science class, you simply hold the dyed strip up next to a pre-printed color chart and find the closest match. And this brilliantly illustrates that this visual matching method isn't just restricted to human blood. These M-Quant colorimetric test strips use the exact same concept to figure out glucose levels in fruit juices and food. Notice how the color blocks range from a pale yellow at 0 all the way to a dark blue at 500 milligrams per liter. You just dip it, wait 1 minute, and compare the color. Same fundamental science, just applied to your morning orange juice. Let's step back in time for Section 5. Early days of glucose testing. Behold the very first blood glucose meter.
This hefty piece of machinery is the Ames Reflectance Meter, or ARM. Patented back in 1971, just look at the size of that dial and the heavy casing. Unlike the sleek little devices we have today, this was primarily meant for use in doctors' offices. Definitely no way a patient was carrying this around in their pocket for home use.
But what strips went into that machine? Dextrosticks. These had actually been around since 1965, well before the electronic meter even existed, meaning they were originally designed entirely for manual visual color matching. Look at this vintage packaging, it's fascinating. They came in a little glass bottle with a metal screw top, completely wrapped in a paper label, holding 25 reagent strips and a small bag of desiccant just to keep out the moisture. Now, if you think using a modern test strip is even slightly annoying, wait until you hear the highly tedious procedure required for early Dexter sticks. The instructions explicitly warn that directions must be followed exactly. First, apply a large drop of blood. Second, wait exactly 60 seconds using a stopwatch. Third, and this part is just wild, you had to quickly wash the blood off with a sharp stream of water from a wash bottle in 1 to 2 seconds, and then gently blot it. Fourth, you had to read the result within 1 or 2 seconds after washing. I mean, imagine the stress of this manual process. Here is the actual Dextrosticks color chart. You literally had a 1 to 2 second window right after hosing the blood off the strip to hold it up to this chart under whatever random room lighting you had and frantically try to interpolate the color block to guess your blood glucose level. It was an incredibly demanding process that left a massive margin for human error.
Finally, Section 6, a shrinking drop of blood.
Let's look at the physical size requirements here. The pad on those original Dextrosticks was roughly 3/8 by 1/4 of an inch. To fill an area that big, the instructions very accurately demanded a large drop of blood. Today's modern strips, however, feature truly microscopic testing areas that require only a tiny, tiny fraction of a drop. So the crucial point here is the sheer scale of miniaturization. Just think about this. Back in the 1960s, you needed a massive 30 microliter drop of blood paired with a 2-minute reaction time. By contrast, modern biosensors require a virtually painless 0.3 microliters, and they read in seconds. It is a stunning, game-changing leap in biomedical engineering and user convenience. Which brings us to the end of today's explainer. We've gone from heavy glass bottles and literally washing blood off paper strips to instant microfluidic readings. It makes you wonder, as biosensors continue to shrink and the chemistry gets even more sophisticated, what complex medical tests will soon fit on a single, practically invisible drop of liquid? The future of personal diagnostics is going to be incredibly exciting to watch. Keep asking questions, stay curious, and thank you so much for learning with me today.